Yeah, Assalamualaikum warahmatullahi wabarakatuh. My name is Ami Mirza, and today I will be presenting my topic for KEK 4003 Introduction to Aerospace Technology. The title of my presentation is From the Sky to the Stars, and our focus today will be on combat unmanned aerial vehicles or combat UAVs. Over the next 60 minutes, I hope to take you on a journey from the earliest experiments with unmanned flight over 100 years ago, all the way to cutting edge technologies like drone swarms and artificial intelligence that are shaping the future of aerial warfare. So, let's get started. Before we dive in, here is a quick overview of what I will be covering today. We will begin with an introduction and definition of combat UAVs, what they are and what they matter. Then we will look at the historical evolution of UAV technology, tracing how drones developed from simple radio-controlled aircraft into the sophisticated combat systems we see today. After that, I will walk you through the MQ-9 Reaper as a detailed case study of a modern combat UAV. We will then explore the technical fundamentals of how UAV systems work, followed by the different type of UAVs and the weapons and payloads they carry. From there, we will look ahead at future directions in UAV development, including AI and drone swarms. And finally, we will cover counter UAV systems, the technologies being developed to defend against drones. So, what exactly is a UAV? UAV stands for Unmanned Aerial Vehicle. At its most basic level, a UAV is simply an aircraft that operates without a human pilot physically on board. Now, that does not mean they fly themselves without any human involvement. UAVs are controlled in one of two ways, either by a remote operator at a ground control station or through autonomous flight control systems that have been pre-programmed with mission parameters. What makes UAVs so powerful is what they carry on board. Modern UAVs are equipped with communication systems, sensors, cameras, and navigation systems, which allow them to perform a wide range of missions, for simple aerial photography all the way to complex military strike operation. Think of a UAV as a highly capable, remotely deployable platform, one that can go places, stay for durations, and take risks that would be impossible or unacceptable for manned aircraft. Now, within the broader UAV category, there is a specific class of drone that we will focus on today, the combat UAV, formerly known as Unmanned Combat Aerial Vehicle or UCAV. A combat UAV is a drone designed specifically for military combat operations. This is important. Not all UAVs are combat drones. Many are used for commercial photography, agriculture, or civilian surveillance. Use UCAVs, however, are built and equipped for warfare. What can a combat UAV do? They are capable of performing missions such as surveillance and reconnaissance, watching the enemy without being seen, target tracking, maintaining a lock on moving targets over long distances, and precision strike operations, delivering weapons with a high degree of accuracy. Perhaps the most significant features of combat UAVs is that they allow military forces to conduct dangerous operations while removing the risk to human pilots. A pilot sitting thousands of miles away at a ground control station can control a drone flying over a hostile territory. If that drone is shut down, no pilot is lost. This is fundamentally transformative shift in how warfare is conducted. Let's talk a little more about why combat UAVs matter. What makes them so important to modern military forces? First, real-time intelligence. UAVs can loiter over a target area for many hours, providing continuous live video feeds and sensor data directly to military commanders. This is called persistent surveillance, and it gives commanders an unprecedented level of situational awareness. Second, cost and efficiency. UAVs are generally significantly cheaper to operate than manned fighter aircraft. A manned jet, like the F-35, costs tens of thousands of dollars per flight hour to operate. A UAV like the MQ-9 Reaper costs a fraction of that. And because UAVs don't need life support system, ejection seats, or cockpit, they can be made lighter and more fuel efficient. Third, long endurance. UAVs can remain airborne for remarkably long period, sometimes over 24 hours on a single mission without rest. A human pilot needs to sleep, eat, and rotate. A drone doesn't. And fourth, reduce risk to personnel. As I mentioned, UAVs significantly reduce the danger to pilots during high-risk missions, whether those missions are over hostile territory, near anti-aircraft systems, or in environments where a manned aircraft would be too vulnerable. Now, let's step back and look at the bigger picture. How did we get here? The development of UAV technology spans more than a century. It did not happen overnight. It evolved gradually through wars, technological breakthrough, and shifting military priorities. Early experiments in the 1900s focused on simple radio-controlled aircraft and basic autopilot systems, crude by today's standards but revolutionary for their time. During World War II and the Cold War that followed, UAVs were mainly used for training and reconnaissance, target drones to train anti-aircraft gunners, and spy drones to gather intelligence. And today, UAVs have evolved into advanced combat systems capable of carrying precision weapons and conducting complex multi-phase military operations. Over the next several slides, we'll trace this evolution step by step. The story of UAVs begins in the early 20th century when engineers first started experimenting with idea of flying machines that didn't require a human on board. One of the very first examples of this was the catering bug. Developed in 1918 during World War One, the catering bug was essentially an unmanned aerial torpedo. It was designed to be launched, fly a predetermined distance toward a target, and then detonate on impact. Now, this was an extremely primitive device by modern standards. It had no GPS, no real-time control, and no sensors. But what is demonstrated was core concept of unmanned aerial warfare. The idea that an aircraft could be used as a weapon without putting a pilot in harm's way. The catering bug never saw widespread use in combat, but its development planted a seed that would eventually grow into sophisticated UAV systems we have today. It is important to appreciate that every revolutionary technology has humble beginnings. The catering bug of 1918 and the MQ-9 Reaper of today are more connected than they might appear. For UAVs to become practical military tools, engineers needed to solve several fundamental technological challenges. Let's look at the key innovation that made early UAV development possible. The first was radio control communication systems. The ability to transmit commands wirelessly to an aircraft from a distance. Without a reliable radio control, you couldn't steer a drone at all. Early radio systems were fragile and had short ranges, but they were the necessary foundation. The second innovation was automatic pilot system or autopilot. This allowed an aircraft to maintain a stable heading and altitude without constant manual input. Early autopilots used simple mechanical gyroscope to detect and correct tilting or turning. This brings us to the third innovation, gyroscope stabilization. By measuring the aircraft's orientation in three dimensions, gyroscope help keep early UAVs on stable flight paths. These three technologies, radio control, autopilot, and gyroscope stabilization, became the building blocks of modern drone systems. Today's UAVs use far more advanced version of these same principles. Digital radio links, sophisticated flight computer, and multi-axis inertial navigation system. The foundation were laid over a century ago. Modern engineers have simply refined and enhanced them. During World War II, the development of UAV technology accelerated significantly as several major nations began investing in unmanned systems for military use. The most common application at this time was the target drone, an unmanned aircraft used to train anti-aircraft gunners. Before UAVs, gunners would train using towed banners or stationary targets. A moving aerial target was far more realistic. The most widely used target drone in the US military was the radioplane OQ-2, which was mass produced in large numbers and used extensively for gunnery training. But World War II also saw the development of something far more sinister, the V-1 flying bomb, developed by Nazi Germany. The V-1 was essentially an unmanned jet-powered aircraft packed with explosives. It was pre-programmed to fly a set distance and then crash into its target. Over 10,000 V-1s were launched at London and other Allied cities. The V-1 is widely considered one of the earliest examples of a guided unmanned aerial weapon. In large-scale warfare, it wasn't precise by modern standards, but it demonstrated the unmanned aircraft could be used as offensive weapon, a concept that would define the next century of military aviation. After the World War II, the Cold War between the United States and the Soviet Union created intense demand for a specific type of UAV, the reconnaissance drone. The challenge was this: both superpowers desperately wanted intelligence on each other's military capabilities, troop movements, missile installation, nuclear facilities. But sending manned spy aircraft into enemy airspace was extremely dangerous. In 1960, an American U-2 spy plane was shot down over the Soviet Union, causing a major international incident. The pilot, Francis Gary Power, was captured. It was a diplomatic disaster. UAVs offered a solution. A drone could fly over enemy territory to collect photographic and electronic intelligence without risking a human pilot. If the drone was shot down, there was no pilot to capture. no prisoners to parade in front of cameras, and no political crisis to manage. And one of the most important examples from this era was the Ryan Fire B, a jet-powered reconnaissance drone used extensively by the US military for intelligence missions. The Ryan Firebee demonstrated that UAVs could perform real, high-stake intelligence missions effectively. The Cold War established UAVs as serious military assets, not just training tools. This shift in perception would prove crucial for future development. The Vietnam War brought UAVs into active combat theater in a significant way. During this conflict, UAVs played an important role in reconnaissance missions, gathering critical intelligence that manned aircraft struggled to obtain safely. UAVs were used to collect aerial photographs of enemy military bases, supply routes, and troop movements. In a conflict like Vietnam, fought across dense jungle, mountainous terrain, and heavily defended airspace, having persistent aerial surveillance was invaluable. The information gathered by these drone reconnaissance missions helped military planners build a much clearer picture of the battlefield, where enemy forces were concentrated, how they were being supplied, and where they were moving. Critically, using UAVs also reduced the number of dangerous reconnaissance flights performed by human pilots. In Vietnam, anti-aircraft fire and surface-to-air missiles were responsible for significant losses among manned aircraft. Every reconnaissance mission replaced by a drone was a pilot whose life wasn't put at risk. The Vietnam War demonstrated that UAVs could operate in real combat environments, under real threat conditions, and deliver genuine military value. This experience would directly inform the next generation of UAV development. One of the most pivotal moments in the history of UAV development came not from the superpowers but from Israel. During the 1982 Lebanon War, Israel deployed a remarkably innovative strategy. They deployed UAVs not as weapons or as simple reconnaissance drones, but as decoys to confuse and fool enemy radar and air defense systems. Here's how it worked. Israeli UAVs were sent into Syrian-controlled airspace first, triggering the Syrian air defense network to switch on its radar systems. Once those radar systems were active and their position revealed, Israeli electronic warfare aircraft jammed them, and fighter jets moved in to destroy them. The result was devastating for Syrian air defenses. Israel destroyed 19 Syrian surface-to-air missile batteries without losing a single manned aircraft. This operation was a watershed moment in military history. It demonstrated that UAVs didn't just have to carry sensors or weapons. They could be used as intelligent tactical tools to shape the battlefield, manipulate the enemy, and create conditions for success. The success of Israel's UAV strategy in 1982 sent shock waves through military establishments worldwide and triggered a global surge in UAV research and investment. The Israeli example in 1982 introduced the world to a concept that remains highly relevant today. Using UAVs for suppression of enemy air defense or SEAD missions, the core idea behind SEAD is straightforward. before you send expensive manned aircraft into hostile airspace, you want to degrade or destroy the enemy's ability to shoot them down. You want to neutralize their radar, their surface-to-air missiles, and their anti-aircraft guns. UAVs are extremely well suited for SEAD missions for two reasons. First, detection. UAVs can be equipped with sensors to detect where enemy radar systems are operating. They can map the electromagnetic environment without risking a human pilot. Second, decoying. UAVs can be deliberately flown in ways that force enemy radar systems to switch on and reveal their locations. Once a radar system activates to track a drone, it immediately becomes a target itself. In both cases, UAV are essentially acting as bait, drawing enemy fire so that human pilots don't have to. Modern SEAD operations often involve a combination of UAVs, electronic warfare aircraft, and anti-radiation missiles working together. The UAV's role in these ecosystems is to provide the initial provocation and intelligence that the rest of the system acts on. Now we arrive at what many historians and military analysts consider the true turning point in modern UAV development: the introduction of the MQ-1 Predator. The MQ-1 Predator was introduced in the 1990s by General Atomics under contract with the US military. What made it revolutionary was not just its surveillance capability, but the fact that it was one of the first UAVs capable of carrying guided missiles. Before the Predator, UAVs could watch. With the Predator, they could act. The drone could now identify a target, track it, and destroy it, all without a human pilot in the air. The Predator was widely deployed in Afghanistan and Iraq following the September 11 attacks, and it quickly became one of the most strategically important tools in the US military's arsenal. Its ability to loiter over a target area for extended periods, provide live video, and then strike when the moment was right changed the nature of counterterrorism operation fundamentally. The Predator proved the concept that a single unmanned platform could perform both intelligence gathering and precision strike operation. This combination, often called the find, fit, finish mission, became the model for all future combat UAV development. Today, we live in a world where many nations operate advanced combat UAV systems, and the technology continues to evolve rapidly. Let me highlight three of the most significant modern systems. The MQ-9 Reaper from the United States is arguably the most capable and well-known combat UAV. It is larger, faster, and more heavily armed than its predecessor, the Predator. We will spend more time on the Reaper shortly. The Bayraktar TB2 from Turkey has become internationally prominent following its effective combat use in conflicts in Syria, Libya, Nagorno-Karabakh, and Ukraine. It represents a new class of affordable, exportable combat UAVs that have given smaller nations access to precision strike capability that was previously the exclusive domain of superpowers. The RQ-4 Global Hawk is a large, high-altitude reconnaissance drone operated by the US military. It can fly at extremely high altitudes for over 30 hours, monitoring vast geographic areas in real time. With all of these modern systems, share is the ability to perform long endurance missions with advanced sensors and, in the case of armed variants, the precision strike capability. Together, they represent the current state of the art and the baseline from which future UAV development will build. Now that we understand the history of UAVs, let's look under the hood. How does a UAV system actually work? A complete UAV system is not just the drone itself. It is a complex ecosystem of interconnected components that must all work together seamlessly. The airframe is the physical structure of the aircraft, the body, wings, and fuselage. Modern UAV airframes are typically made from lightweight composite materials to maximize endurance and payload capacity. The propulsion system provides the thrust needed for flight. This may be a jet engine, a turboprop, or an electric motor, depending on the UAV's size and mission requirement. The flight control systems is the brain of the aircraft. It is processes input from the operator or from autonomous programming and translates them into control surface movements that guide the aircraft. The communication systems is the link between the drone and its operators. We will look at this in more detail in the next slide. The payload is whatever the UAV is carrying: cameras, sensors, weapons, electronic warfare equipment, or combination of these. And finally, the ground control system, which I will cover shortly, is the command center from which operators manage the entire mission. Understanding that a UAV is a system, not just a vehicle, is essential to appreciating both its capabilities and its vulnerabilities. Of all the components in UAV system, the communication system may be the most critical. Without reliable communications, a UAV is essentially useless. Communication systems serve two primary functions. First, they allow operators to send control commands to the aircraft to change its direction, altitude, speed, or trigger weapons. Second, they allow the aircraft to send data back: live video from cameras, sensor readings, GPS position, and telemetry about the aircraft's health. UAV communication can operate on two types of links. For short to medium range operations, UAV typically use radio frequency links in the VHF or UHF or microwave bands. These links are fast and low latency, ideal for precise control. For long-range operation, particularly for aircraft operating beyond line of sight, satellite communication systems are used. Satellite links allow operators to control drones on the other side of the world. The MQ-9 Reaper, for example, is often flown by pilots based in Nevada who are controlling aircraft over Afghanistan or Iraq via satellite. The vulnerability of communication systems is also an important military consideration. Signal jamming, transmitting interference to disrupt a UAV's communication link, is one of the primary methods used by adversaries to neutralize drones. This is why secure, encrypted, and redundant communication systems are a high priority in UAV design. Let's talk about the Ground Control Station or GCS, the place where human operators actually manage UAV missions. A ground control station is essentially a sophisticated command post. Think of it as the cockpit, except instead of being surrounded by sky at 30,000 feet, the operator is sitting safely on the ground, often thousands of kilometers from the drone. The GCS provides operators with several key capabilities. It gives them a real-time interface for controlling the aircraft, navigation, speed altitude, and systems management. It displays live flight status, fuel levels, engine health, GPS position, and communication link quality, and it provides access to live video feeds and sensor data from the aircraft's payload cameras. Operators also use the GCS to plan mission, pre-programming routes and waypoints before a flight, and making adjustments as conditions change. For large, strategic UAVs like the Global Hawk or Reaper, a ground control station may be a permanent facility with multiple operators, one flying the aircraft, another managing the sensors, and a third coordinating with military commanders. It is a team effort. The ground control station represents the human element in UAV operations, the point at which human judgment, ethics, and decision making remain part of the equation, even as automation increases. Not all UAVs are the same. They come in a wide range of sizes, capabilities, and configuration. Designed for very different mission and operating environments, UAVs are generally classified into several categories. Micro UAVs. These are very small drones, sometimes small enough to fit in a soldier's backpack. They are used for short-range reconnaissance at the tactical level. A soldier in the field launching a drone to see around the next corner or over the next hill. Tactical UAVs, medium-sized drone, used by military units for battlefield reconnaissance and electronic intelligence. They typically have a range of tens to hundreds of kilometers. Medium altitude long endurance, as known as MALE UAVs. These are the class that includes a famous system like the MQ-9 Reaper, the Bayraktar TB2. They operate at medium altitude, can stay airborne for many hours, and often are. High altitude long endurance, HALE UAVs, large sophisticated drone that operates at very high altitudes, commonly above 50,000 feet. For extremely long durations, the RQ-4 Global Hawk is the prime example. Each category occupies a distinct role in the military's layered intelligence and strike architecture. Let's look at a little more closely at the medium altitude long endurance class, since this is where many of the most operationally significant combat UAVs belong. MALE UAVs are designed to operate at medium altitudes, typically between 15,000 and 45,000 feet, for extended periods of time. Their combination of endurance, sensor capability, and in many cases, weapons capacity makes them the workhorse of modern combat UAV operations. The defining feature of male UAVs is exactly what the name suggests: endurance. The ability to stay airborne for long periods allows these drones to maintain persistent surveillance over a target area, wait for the right moment to strike, and provide continuous support to ground forces. The MQ-9 Reaper is the premier example. It can remain airborne for more than 24 hours on a single mission, carrying a combination of advanced sensors and weapons, including Hellfire missiles and precision-guided bombs. For military commanders, a male UAV like the Reaper is an extraordinarily valuable asset. It provides continuous intelligence, can respond to time-sensitive targets, and is always available, day or night, in almost any weather condition. At the upper end of the UAV spectrum, we have the high altitude long endurance class, the giants of unmanned aviation. HALE UAVs operate at very high altitudes, above 60,000 feet in some cases, which places them far above most anti-aircraft threats and allow them to surveil enormous geographic areas from a single position. Their primary missions is strategic surveillance and intelligence gathering. They are modern equivalent of the Cold War spy plane, but without a human pilot. The RQ-4 Global Hawk is the most well-known HALE UAV. It has a wingspan of nearly 40 meters, comparable to a Boeing 737, and can fly over 30 hours without refueling. From its operating altitude, the Global Hawk can monitor an area the size of South Korea in a single day. HALE UAVs are not typically armed. Their value is in intelligence, not direct combat. They feed data to commanders, analysts, and lower-level combat assets like male drones that can then act on that intelligence. Think of a HALE drones as the eyes at the top of the hierarchy, providing broad strategic awareness which male drones zoom in on specific target. A UAV is only useful as the sensors it carries. Let's look at the key sensor types that make modern combat UAVs so capable. The first is electro-optical cameras. These are essentially very powerful digital cameras capable of capturing high-resolution imagery in the visible light spectrum. Modern EO cameras on drones can identify a person or vehicle from tens of thousands of feet in the air. The second is infrared sensors. These detect heat signatures rather than reflected light, which makes them enormously valuable at night or in low visibility conditions. A person hiding in a bush is nearly invisible to an EO camera at night, but their body heat makes them instantly visible to an infrared sensor. This is why UAVs can conduct effective operations around the clock. Radar systems. Some of UAVs carry synthetic aperture radar, which can detect objects and movement on the ground, even through clouds, rain, or foliage. Radar surveillance can be done from standoff distances that make the drone nearly impossible to detect. Laser targeting devices. These are used to paint or designate a target with a laser beam. A precision-guided munitions, bombs, and missiles can then home in on the laser spot with extraordinary accuracy. This is how a modern UAVs achieve the precision that distinguish them from the area bombing of past conflicts. Together, the sensor suites give modern UAV an unprecedented ability to find, identify, track, and target with minimal risk to human operator. Let's now talk about what armed combat UAVs actually carry into battlefield. Combat UAVs can be equipped with different types of weapons depending on their mission. The general principle is same as with manned strike aircraft. The aim is to deliver lethal effect on target with precision and minimal collateral damage. The most common weapon carried by combat UAVs is the AGM-114 Hellfire missile. Originally designed for attack helicopters, the Hellfire has been adapted extensively for use by drones. It is a relatively small, laser-guided missile with a shaped charge warhead ideal for destroying vehicles, equipment, and hardened position. The Hellfire is the signature weapon of the MQ-9 Reaper. UAV also carry laser-guided bombs, gravity bombs with laser guidance kit that allow them to be steered into a designated target with meter-level accuracy. And there are various precision-guided munition, smaller, lighter weapons designed specifically for the UAV's environment, where size and weight constraints are significant. The key word in all of this is precision. The combination of sophisticated sensors, laser designators, and guided weapons mean that modern combat UAVs can strike with a level of accuracy that was unimaginable even 30 years ago. Combat UAVs are not single-purpose tools. They can perform a wide range of military missions, which is one of the key reasons they have become so central to modern military operations. Intelligence, surveillance, and reconnaissance is perhaps the most common mission. UAVs loiter over an area of interest, collecting imagery and signals intelligence that is fed directly to commanders and analysts. Target identification. In complex environments where combatants and civilians may be mixed, the persistent surveillance capability of UAVs allows operators to observe targets over extended periods before making strike decisions, reducing the risk of misidentification. Precision strike operation. Using the weapons we just discussed, UAVs can engage time-sensitive targets quickly and accurately. Border monitoring. Many nations use military-grade UAVs to monitor national borders and maritime exclusive zones for illegal crossings, smuggling, and hostile incursions. What makes UAVs so valuable across all of these mission types in their combination of long endurance, multi-sensor capability, and the ability to transition from surveillance to strike, all in a single platform, without ever putting a human pilot at risk. Now, let's look forward. Where is UAV technology headed? The next frontier is autonomy and the artificial intelligence that makes it possible. Today's combat UAVs are still primarily human controlled. A pilot sits at a ground control station and makes the key decisions: where to fly and when to strike. Automation helps with navigation and flight stability, but the human remains firmly in the loop. Future UAV systems are expected to change this fundamentally. Advanced autonomous capabilities will allow drones to perform tasks like automatic navigation, target detection, and even mission planning with minimal human intervention. The drone will be able to take off, fly to an area of operations, identify targets, and return to base all on its own. Artificial intelligence is the technology that will make this possible. AI systems are being developed that can help UAVs perform objective recognition, identifying specific types of vehicles, weapons, or personnel from sensor data, path planning, calculating the optimal route through complex contested airspace, threat analysis, evaluating risk in real time, and adjusting mission parameters accordingly. The ethical implication of autonomous weapons, that can select and engage targets without human authorization, are a major area of international debate. We will touch on this in the challenges section. One of the most fascinating and potentially alarming emerging technologies in the UAV space is drone swarm technology. A drone swarm involves multiple UAVs operating together as a coordinated group. Rather than one drone doing one job, you have dozens or even hundreds of drones acting collectively, communicating with each other and dividing tasks in real time. Think of it like a flock of birds. Each individual follows simple rules, but together the group exhibits complex, intelligent behavior. In a military context, drone swarms offer several powerful advantages. They can attack from multiple directions simultaneously, overwhelming enemy defenses. They can share sensor data between platforms, creating a collective picture that is richer than anything a single drone can provide. If they can adapt, if one drone is destroyed, the swarm, the swarm reconfigures around the loss and continues the mission. One of the key advantages of swarms is that they are difficult to defend against. Traditional air defense systems are designed to track and engage one, two, perhaps a handful of targets simultaneously. A swarm of 50 or 100 drones attacking simultaneously can saturate and overwhelm even the most advanced system, uh, even the most advanced defense systems. Several nations, including the United States, China, and Russia, are actively developing drone swarm technology. It is expected to play a significant role in the future conflicts. Another exciting development at the frontier of UAV technology is the loyal wingman concept. The idea here is elegantly simple. Instead of replacing human fighter pilots with autonomous drones, what if drones could fly alongside and support manned aircraft? In the loyal wingman model, UAVs fly in formation with manned fighter like the F-35 or F-22 Raptor. These drones are not fully autonomous weapons. They are partners and force multipliers for human pilots. What can loyal wingman drones do? They can perform reconnaissance ahead of the manned aircraft, mapping tracks before the human pilot enters the danger zone. They can conduct electronic warfare by jamming enemy communication and radar. They can act as a decoys, drawing enemy fire away from the manned aircraft. And in some configuration, they can carry additional weapons, effectively extending the manned aircraft's magazine capacity. The loyal wingman concept is already being tested in prototype form by several nations. Australia's Boeing MQ-28 Ghost Bat and the US Air Force's Collaborative Combat Aircraft Program are leading examples. This approach reflects a nuanced vision of the future of aerial warfare, not one where machines replace humans, but where machines and humans operate as an integrated team, each doing what they do best. With UAVs becoming so prevalent and capable, it's no surprise that there's a rapidly growing field dedicated to defeating them. Counter UAV or CUAV technology. As UAV use increases across both state and non-state actors, many countries are investing heavily in systems to detect, track, and neutralize hostile drones. The counter UAV toolkit includes several distinct approaches: radar detection technologies, specialized radar systems designed to detect the small radar cross sections of drones which traditional air defense radar often miss. Electronic signal jamming, transmitting interference on the frequencies that drones use for control and navigation, causing them to lose guidance or crash. Laser weapons, high energy directed energy weapons that can burn through a drone's airframe or destroys its sensors. Laser systems are attractive because each shot costs almost nothing compared to a missile. Interceptor drones, deploying a small fast UAV to physically intercept and ram a hostile drone or to drop a net over it. Counter UAV technology is now a key priority for military forces around the world. The proliferation of affordable commercial drones that can be modified for military use, as seen extensively in the Ukraine conflict, has made C-UAV or counter-UAV capability essential not just for national militaries but for forces at every level. As we near the end of our presentation, let's reflect on the challenges that UAV technology still faces and where the future is headed. On the challenges side, there are several significant issues. The first one is vulnerability to jamming and electronic warfare. As I mentioned, disrupting a UAV's communication link can neutralize it. Adversaries are getting increasingly sophisticated at jamming, spoofing GPS signals, and hacking drone systems. The second one is cybersecurity threats. A networked UAV system is a potential target for cyber attacks. If an adversary can penetrate a UAV's command and control network, they could potentially take over the drone, feed it false sensor data, or simply shut it down. Ethical and legal concern, particularly around autonomous weapons systems. Who is responsible when an autonomous drone makes a mistake and kills civilians? The legal and ethical frameworks to govern autonomous lethal systems are still being deployed. Financial costs. While UAVs are cheaper than manned aircraft to operate, developing cutting-edge UAV systems still requires enormous investment in research, testing, and infrastructure. Looking to the future, however, the trajectory is clear. UAV warfare will continue to evolve toward greater autonomy, AI integration, and coordination between unmanned and manned platforms. Drone swarms will become a standard part of military arsenals. Loyal wingman programs will mature. Counter UAV technology will develop in parallel. UAVs will become even more deeply integrated with satellite networks, cyber operations, and battlefield management systems, part of a vast interconnected machine of modern warfare. And on that note, I would like to bring my presentation to a close. Today, we have covered a lot of ground, from Catering bug of 1918 to the drone swarms and AI system of the near future. We have explored how UAV technology evolved through wars and geopolitical tensions, how modern systems like the MQ-9 Reaper work and what makes them so capable, and where this technology is likely to take us. The story of UAVs is really a story about humanity's constant effort to reduce risk while increasing capability, to project power without sacrificing human life. That drive is not going any away. If anything, it is accelerating. I hope this presentation has given you a clearer understanding of what combat UAVs are, how they got here, and why they matter. Thank you very much for your attention.